The Vernier flash photolysis spectrometer is a transient absorption spectrometer designed for measuring photochemical reactions in the college laboratory. Transient absorption spectroscopy is a vital component of a college chemistry curriculum. The field of photochemistry is ever expanding into new applications, with its influence touching so many different disciplines, including its use in a recent Nobel Prize in laser physics. It is quickly becoming an essential topic for undergraduate chemistry majors. Examples of fast photochemical reactions appropriate for the teaching laboratory include investigating excited state dynamics, triplet state phosphorescence, cis-trans isomerization, reactive free radicals, and photocatalysis. The Vernier flash photolysis spectrometer is an affordable, time-resolved spectrometer used for studying these fast, light-induced reactions. A block diagram of this system appears on the top of the instrument to illustrate the pump probe design. In this system, a xenon flash lamp provides the photoexcitation pump pulse. A colored glass filter selects down the excitation wavelengths that interact with the sample, which is placed here. Then a white light from an LED light source probes any spectral changes made in the system by the excitation light pulse. The white light from the LED source is focused on the sample. From the sample, this light beam carrying the change in absorbance goes through a focusing lens and then a wavelength dielectric filter while being focused onto the photodiode, which detects the light's intensity. If the flash lamp causes changes in the absorption of the filter's wavelength, the detector will measure these changes. The current from the detector is collected, digitized, and stored versus time in a comma-delimited file, which may then be analyzed in any third-party software, including Logger Pro or graphical analysis. To use the Vernier flash photolysis spectrometer, first download the free software from our website. From here, you can see the photodiode level, the experiment type, the time window, the number of samples to average. You can also collect data and save it. This second generation of the flash photolysis has quite a few advantages for an educational flash photolysis spectrometer. For one, the instrument is powered completely off of the USB port from the computer, so there's no need for a separate external AC power supply. It also comes with multiple filters to select excitation and emission wavelengths that help ensure you're getting the cleanest light excitation and detection. The reaction I will be demonstrating today is one of the free experiments available on our website, and it is a very approachable experiment for undergraduate students. It explores the excited state cis-trans isomerization of Congo red and its substituted carbon-carbon double bond. Congo red undergoes a trans to cis isomerization under excitation with visible light. The kinetics of this reaction are much too fast to be seen on the microsecond timescale we have here. However, the excited cis state will thermodynamically relax back to the trans state on the microsecond timescale. Moreover, the rate is found to be catalyzed by both acids and bases, so the student can find the bimolecular rate constant for catalysis by hydroxide ions. I've prepared the Congo red sample as described in the experimental setup. The instrument is on and it's registering light as I've inserted the filters in the sample. I'm using the 580 nanometer dielectric filter for this experiment. Using this filter will allow me to see the kinetics of the photoreaction at the desired wavelength for this compound. I'd also like to use a filter that narrows my excitation window and use the CGBG3 excitation filter, which filters out the ground state absorbance of Congo red at around 500 nanometers. For this experiment, I've extended the time window to 500 milliseconds, and for preliminary runs, 3 averages is sufficient. The more averages you collect, the less noisy your data will be. So now I'm going to go ahead and press run and collect some data. You can see the flash lamp going off. And now we have some beautiful kinetic data. You can also see a strong instrument response function at time equals 0. Now that I'm done, I can zoom in on the kinetic trace for the Congo red, and just quickly glancing, I would say that is a time constant of around 100 milliseconds. But as I export the data into another party software, I can use an exponential fit and get an exact rate constant for this reaction. Then I can add some sodium hydroxide to my sample and see how much the base catalyzes that reaction and get those exact rate constants. This instrument is great for physical chemistry, biochemistry, inorganic chemistry, and instrumental analysis courses. It is also ideal for student projects. For more information, see our website or email chemistry@vernier.com.